Hello. This is Nicholas. I'm just going to jump right into it because I'm low on time, and so are you guys, I'm assuming. So we have our exam tomorrow, and this is, if you type in AP Calc BC Practice Exam 2020, this is what pops up. This is the first of the two questions that we'll get for this year, and so this one is going to take us 25 minutes in theory. I haven't done this question, so it'll be my first time doing it. So I'm going to just go through how I would do it, and that'll be that. So, okay, it is about basically 1:30, so hopefully I'm done by 1:55. Okay, number one. Okay, so we have this, it's a continuous function. We have this here. Okay, we want to find that area. Integral from negative 6 to 5 of f of x dx. So we're only given from negative 2 to 5, and we know this is what we want to find. So what we can say is that the integral from negative 6 to 5 of f of x dx is equal to the integral from negative 6 to negative 2 of f of x dx. That's what we want to find, plus the integral from negative 2 to 5. So I've just split the area at negative 2 of f of x dx. And so that means that we want to find from negative 6 to negative 2. So the integral from negative 6 to negative 2 of f of x dx is this first integral here, which they tell us is just 7. So I'm just going to write 7 minus the integral from negative 2 to 5 of f of x dx. And I'm thinking we're just going to be able to compute that just by looking at areas here. So we have the integral from negative 2 to 5 of f of x dx. So now, what am I going to do to compute that? So first, I'm just going to look at this graph. And so we have from a negative 2 to a 5. So I say to myself, well, I need this area. I'm going to try to be as lazy as I can here. See, I need this area right here. But then I notice I'm also going to need this area. Well, these areas are going to just cancel out. So they're going to give me a net of 0. So I don't even need to calculate those. Now I notice I'm going to need this area right here, but then I notice I'm also going to need this area right here. So those are also going to cancel out, and so I don't need those as well. Now what I am going to need to calculate is I'm going to need to calculate this area right here, and then this area right here below what looks like this circle. So what I'm going to do is I'll break it up. So right here we have just a unit square, so that's of area 1. Then we have this triangle right here with a height of 2 and a base of 1. So the area of that triangle is just going to be 2 times 1 times a half, or just 1. So that area, that triangle is 1. Now they tell us something about this circle. It's a quarter circle centered at the point 5,3, so that's its center right here. So that means that, now here's how I'm going to think about this. The area of this whole box right here is 9 because it's a 3 by 3 square. So if I consider this box, I can find the area of this quarter circle, 1/4 pi r squared, and then take that area and subtract it from our total area of 9 of this whole box, and that will give me this area under this like arc of this quarter circle. So the area of the box is 9. The area of the quarter circle is 1/4 pi times 3 squared, which is 9. So we have 9 minus 9 pi over 4. And this is going to be this area right under this arc right here. So what do we have? We have 1 plus 1 plus 9 minus 9 pi over 4. So we come back to here. We replace this with a minus, and then we have 1 plus 1 plus 9 minus 9 pi over 4. Okay, so that's going to give us an 11 here. 7 minus 11 is a negative 4. And then we have minus a negative 9 pi over 4. So we're going to get 9 pi over 4 minus 4. And that's going to be our answer for A. Hopefully I didn't butcher that too bad. Okay, I'm going to erase this now because there's more. Okay, so now we're doing B. That's the integral from 3 to 5 of 2f prime of x plus 4 dx. And now what I can do is I can split this up. I'm going to use the fundamental theorem of calculus, so I'll make it 2 times the integral from 3 to 5 of f prime of x dx plus the integral from 3 to 5 of I'll just make it 4 times that of dx. And now using the fundamental theorem of calculus on that integral, that is going to be 2 times f of x evaluated from 3 to 5 plus just 8. Yeah, because you're going to integrate, you get x, you evaluate that from 5 to 3, you get 2, 4 times 2 is 8. Okay, so now f of 5 is, what is f of 5? F of 5 is this point right here, that's just 0. Okay, so 2 times 0 minus f of 3. They tell us that the point 3 comma 3 minus root 5 is on there. So f of 3 is 3 minus root 5. So we have negative 3 minus root 5, or negative 3 plus root 5, plus 8. And so that's going to give us 2 square root 5. And then we have minus 6 from here. But then we have plus 8, so that's a plus 2, which I'll write as 2 times square root 5 plus 1. And that's our answer for B. That looks right to me. Okay, I'm going to do C now. Okay, function g is given by that. Find the absolute max of g on that interval. So I want to find the absolute maximum. I need to take the derivative. I need to set it equal to 0. And I need to find my critical point. So g of x is this. That means by the fundamental theorem of calculus that g prime of x is just going to be f of x. And we need to set that equal to 0 to find our critical point. So we're basically asking ourselves, when is this function 0 on negative 2 to 5? So we have a critical point. Let me erase this stuff because I'm done with this problem now. We have a critical point here. That's a 0. That's a 0. And then this is a 0 right here. Okay. And so now we just need to plug those critical points in to into G, because that's what we're finding the absolute maximum for. We need to just plug those critical points into G, and then we're going to get our answer. We're just going to pick the largest value. Okay, so this point is obviously the point x equals negative 1. This point right here, x equals negative 1. This is x equals a half, and this is x equals 5. So those are our critical points that we're going to plug in. So and honestly, you don't even really need to plug in all of them, right? Because notice, okay, well, I'll just plug it in just for being complete, I guess. Okay, so g of, what are we plugging in? G of negative 1, that's going to be the integral from negative 2 to negative 1 of f of t dt. And we can just look at this up here, and we can say that is a triangle, a right triangle with a height and a base of 1. That means its area is a half. So this integral here is a half. We need g of a half. That's going to be the integral from negative 2 to a half of f of t dt. And again, we're going to look at this, and we're going to say what is that in terms of area. So notice that this here, that rectangle, is going to cancel out in area with this rectangle here. And so we're going to be just left with finding the area of this small right triangle here. And so that triangle has a height of 1, a base of a half. That means its area is a fourth. And so that's the answer to that integral. Now g of 5 is the integral from negative 2 to 5, which I think we calculated before in a previous problem. Negative 2 to 5 of f of t dt. So that integral is, oh yeah, we calculated all that before. Remember, that was 2 times square root 5 plus 1 from part A. We needed to calculate that in part A. So, yeah. And even if you don't know what it is, you notice that just by looking at this, you can say, well, let me erase this here. Yeah, we did calculate that before, but notice you can just say that this area right here, it's going to cancel out with this area right here. And then this is going to be just a little negative area right here. But this is going to be a lot more positive area. And then we're going to get even more positive area right from here under this circular arc. So notice that it makes sense that at x equals 5, we have a maximum of g, and that maximum was given by a calculation before, 2 times square root 5 plus 1. So that takes care of part C. Okay, now I'm going to do part D. This just looks like we're just going to have to plug in some stuff. It really doesn't look that bad. 10 to the x is continuous, so we can just plug that in. Okay, so this is the limit. Let's write some stuff out first. 3f prime of x. So notice that we're approaching 1. And so this, again, this function f is continuous. So I'm basically going to be looking at this segment right here, this line segment. That's what I'm going to be considering here. And notice that this line segment, it's got an equation given by y equals 2x minus 1 because its slope is 2 and its y-intercept is negative 1. If that's f of x along that neighborhood, then f prime of x is just 2. So we have 10 to the 1 minus 3 times 2 over f of x. And again, f of x in that neighborhood is just 2x minus 1. And since we're directly substituting, I'll just put 2 times 1 minus the arctan of 1, which is, if you remember, pi over 4. And I don't even need the limit here because I've already evaluated it. So we just have 10 to the 1. We have all that. That's going to be 10 to the 1 is just 10. 3 times 2 is 6 over, oh, that was a 2 there. 2 times 1 minus 1. That's 1 minus pi over 4. And so we get 4 over 1 minus pi over 4. And I don't think they would want you to simplify it any farther than that, but I can make this 4 over 4. So I can make it 4 over 4 minus pi. Times a 4 here, so that's 16 over 4 minus pi. You could have left it either way, whichever way you prefer. That takes care of parts A through D. Oops, I meant to get the eraser there. Okay, now we're going to move on to E through G, and this is all in 25 minutes. Okay, a portion of this graph here is shown. I want the third degree Taylor polynomial for f about 0. Recall that general formula for the Taylor polynomial f of x is the sum n equals 0 to infinity of f. If we're centering at 0, it's just going to, okay, well, in general, let's say we had it centered at x equals a, just for some constant a. We'd have the nth derivative evaluated at a times x minus a to the n, and that's all going to be over n factorial. There are a number of, and I could probably do a video on this, but you're probably not interested in a derivation of this formula this close to the exam, but there are a number of wonderful reasons why this formula is true. At this point in the game, I would just honestly memorize it. I can't believe I'm saying that to myself, but that's what I would do at this particular point. Anyway, so here we have a equals 0, so this formula just reduces to f of x is sigma n equals 0 to infinity of f sub n, or I'm sorry, not f sub n, the nth derivative of f evaluated at 0 times x to the n all over n factorial. And now we need to write the third degree Taylor polynomial, so that means we need to have an x cubed. We need to go up to an x cubed. So first of all, expanding out this series up to x cubed, we just get the 0th derivative of f evaluated at 0. That's just f of 0. Plus the first degree term, that's going to give us the first derivative of f evaluated at 0 times an x over just a 1 factorial, that's still a 1. So we just have f prime of 0 times x plus, we're then going to get an f double prime of 0 times x squared over 2 factorial, or just 2, plus our last term is going to be given by f triple prime of 0 times x cubed over 3 factorial, which is 6. And now it just comes to plugging things in. So what is f of 0? Looking at the graph here, f of 0 looks to be at 3 plus f prime of 0 times x. So f prime of 0, notice that they've given us this tangent line here. So we just need to find the slope of this tangent line, and that's going to be f prime of 0. So the slope of this tangent line, notice it is negative 2, right? Because for every 1 unit I go across, I go down negative 2. So that's a slope of negative 2. So we have 3 minus 2x, plus now we are going to use this table here. So plus f double prime of 0. F double prime of 0 is this 3 right here because the n is the order of the derivative. So we get plus 3x squared over 2. Now f triple prime of 0 is, when we simplify it all, we're going to get negative 23x cubed over 12 because we have a 6, but then we're also dividing by that 2 right there. And so that is the answer to part E. Okay, now we're just going to find an approximation for h prime of 1. So, or h of 1. So h of 1 is the integral from 0 to 1 of f of t dt. Well, what is f of t dt based on our approximation? Technically, okay, this is a minute detail, but they're using dt here only because we have a dummy variable. Like t is our dummy variable because we're plugging in x, and that's like our independent variable of our integral bound. So whether you write 3 minus 2t plus 3t squared over 2, or you use x's instead, it doesn't matter. It's a definite integral. It's going to be a number. It's variable independent. So I'm just going to use x's since I have x's up there. So we have the integral from 0 to 1 of 3 minus 2x plus 3x squared over 2 minus 23 over 12x cubed, and that's all dx with respect to x. So now I'm going to take the antiderivative of each one of these. So we get 3x minus x squared. Plus, when we take the antiderivative, we're going to have a 3 on the denominator. That's going to give us a 2 times 3 and a 3 on the numerator. So we're going to have plus 1/2 x cubed. And then minus, then I'm going to have on the denominator there, that next term, 12 times 4 on the denominator over 23 on the numerator. 23 is prime, so I can't factor that any. So 23 over 48 x to the 4th. And that's going to be evaluated from 0 to 1. And notice we kind of can just ignore 0 because every term has a factor of x in it. So when you plug in 0 for x, everything goes to 0. So we really just need to plug in 1, and that's going to be our approximation. Okay, so when we plug in 1, we're just basically summing up these coefficients. So we have 3 minus 1 plus 1/2 minus 23 over 48. And I'm pretty sure they will let you leave it at that. I guess for the sake of completion, 3 minus 1 is 2 plus 1/2, that's 5 halves. 5 halves minus 23 over 48. And I can multiply that first fraction by 24 over 24. 5 times 24 is, I happen to know, 120. So we get 120 minus 23. That's 97 over 48. And maybe that simplifies some more, but I'm going to leave it at that. Okay, now we have part E. Hopefully I can fit that in kind of down here. This is kind of an oddball question to me because it doesn't fit in anywhere with this Taylor approximation stuff. But notice that this integral is actually the reason why the P-series test for convergence that's what it comes down to, is evaluating this integral for P greater than 0. Notice intuitively that if P is greater than 0, then we're going to have x to some positive power. So in other words, we're going to have x cubed or x to the 4th or something. And so as P gets bigger and bigger, the function goes to 0. And so notice that if P is greater than 0, this is going to converge to some number. Okay, so now what is it going to actually converge to? Well, it's going to be in terms of P, obviously. So if we take this integral, now notice, I personally hate doing this, but this is something AP likes, because you plug in infinity anyways. It's bad notation, but I mean, really, who cares? So they want you to take this infinity, since infinity is bad notation, and they want you to write it as following. So they want you to write it as the limit as a approaches infinity of the integral from 1 to a. I mean, it's really saying the same thing, but, you know, whatever AP wants, right? And so now what I'm going to do is I'm going to make this 1 over x to the p plus 1. I'm going to make it x to the negative p minus 1. Negative p minus 1. So in other words, I've just reciprocated the power, made the power negative. So now what I can do there is I can just take that antiderivative. So I'm going to get the limit as a approaches infinity of this antiderivative. So we get when we take the antiderivative here, we get x to the negative p over negative p, evaluated from 1 to a. And so now what I can do is just split this up. Oh, there's Kirill. Kirill, I'm rooting for you, dude. If you watch this video, I hope you do well. Okay, anyway, we just have the limit as a approaches infinity of 1 over, I'll write it as negative 1 over p x to the positive p, so I put the p in the denominator, minus, and now I don't need another limit here for the second lower bound of integration because, again, it doesn't depend on a. I'm only evaluating a on this first part here. So now we have, and it would actually be wrong to put the, well, don't put the limit. Okay, so now we have minus, and then we're going to let we're going to let x be 1 here. So when we plug in x equals 1, we get 1 to the negative p. That's just 1 that's just 1. And so we have minus a negative 1 over p, 1 over negative p, so that becomes a plus. That becomes a plus 1 over p, right? Because we have minus a negative 1 over p, so that's plus 1 over p. And now taking a look at this limit here, as a approaches, my bad. So as a gets bigger and bigger for x, right? As we have this a right here, we're evaluating. I should have put an a, my bad, because I plugged in a here. So now, whenever we let a increase without bounds, a to the p is going to get bigger and bigger and bigger, and then so therefore 1 over a to the p is going to go to 0. And so this whole thing here goes to 0. And in the end, we get an answer of 1 over p. And that's our final answer for part G. And thank God there's no more. This honestly seems harder to me than the normal AP exams because it just seems like I'm comfortable with this stuff, but for someone who isn't, it seems like a lot to do and not much time. Now, I'm explaining my thought process. Normally, I would do this quicker, but still. I will post the 15-minute question up right after this, and I wish you all the best of luck. And if you're feeling down, I don't even have my book because it's stuck in Mr. Mac's room, so